Swayam Prabha. Digital India. Educated India.
Okay, so we are going to begin with the first law of thermodynamics, that today we are going to talk about heat and work and adiabatic changes. So before we go into the details, we'll look into what work, heat and energy means. So when we talk about a system which we are going to deal with in this today's class or for henceforth, we are going to be restricting our discussion on ideal gases and a closed system. So when we are talking about work, we are talking about ideally moving of a piston in a cylinder, frictionless piston moving in a cylinder which is filled with gas. And this gas is supposed to be ideal. Now, what happens when you have various processes? How can we visualize that cylinder? If you have an isochoric process, that means the process has a fixed volume. For that sort of a process, what you have to look into is, suppose you have a cylinder, then you have to have a pin which is going to lock the piston so that its movement is restricted. So this way you can control the volume. Okay, and now if you have an isothermal process, that means the temperature of the system has to be maintained constant. Suppose the gas is expanding, the temperature is going to fall. Suppose the gas is contracting, the temperature is going to increase. So to maintain the temperature constant, what you have to do, this system is supposed to be always in an insulated condition. Only the bottom part is going to be able to transfer an energy through the bottom. So if this bottom is thin, if you can have a temperature which is if you are in contact with the flame, then if there is a temperature drop, the heat can transfer from the source to into the gas and maintain the temperature constant. Similarly, if you have a temperature rise, you can make it in contact with the with ice or cold body, then the whatever temperature is excess can be thrown off from this the bottom part to the surrounding. So how do we and obviously if you have an adiabatic process, then the entire system is going to be uh, such that completely insulated and there's going to be no heat flow from the system to the surrounding. Now when we are doing work, what is actually happening, when we have discussed work previously also in the last class, what we had talked that the movement of the piston. Now, how do we visualize what is going to push the piston down or push the piston up? What we always need to remember that we have to imagine a weight sitting on the lid, and this weight decides the pressure exerted on the gas. Okay, so this is the background you should have in mind. I'm going to discuss what this mass is going to be. This is going to decide whether the work is done on the system. Work is done on as the mass moves up. When the expansion is taking place, what will happen? This will go up. So you see the weight is lifted up. When you're having expansion, you can visualize from this the gas piston is going to move up and the weight sitting on the top is going to be lifted up. Similarly, when you are working on the system, then what happens? You're pushing the piston down. Along with it, the weight on the lid, sitting on the lid, is going to come down. So work is manifested as a weight moving up and down in the surrounding. If it is going down, then it is a compression. If it is moving up, then it's an expansion. So lifting of the weight in the surrounding is the way we explain work. So when we are talking about heat, heat is transferred between the system and the surrounding by the virtue of the temperature difference. And heat is, as we have already discussed, is not a state function, it's path dependent. Heat can be transferred reversibly or irreversibly. And how do you do it when you do it reversibly? You see, you have a system where you can transfer energy in the form of heat through the body, where you can have the energy transfer for a diathermic wall, then the energy can be transferred. And if you want to carry out the process reversibly, then you have to maintain such that the difference between the temperature of the two bodies, system or the surrounding or two bodies, are very, very small, infinitesimally small. Only then you can carry out reversibly. Now, what is work and what is heat? How do you define work and heat? Work and heat are not energies. These are processes of transfer of energy across the system boundary. Energy of a system is the capacity to do work. Work, what is it? Work always generates an organized motion against an opposing force. So whenever work is done by the system, that means the system is doing work. That means it's an expansion process. It is equivalent to rising a weight somewhere in the surrounding. As we had said, it being this, if it is expanding, the weight is rising in the surrounding. Okay. So the work done by the system is equivalent to rising a weight somewhere in the surrounding. When work is done on the system, then you can understand it's a compression. The lid is going to come down along with the lid, with the weight on the lid is going to come down. So the energy of the system is reduced, and it is less when you have a work done by the system. What do you mean by work done by the system? The energy of the system is supposed to go reduce because it is expended in doing the work. It can do less work than before, obviously, when you have done some amount, when the piston is moved out of the spring or unwinding of a spring. Okay. What about work done on the system? What you can visualize work done on the system, on any otherwise isolated system, for instance, by compressing the gas or winding a spring, similar to that, is equivalent of lowering a weight somewhere in the surrounding. It's a compression. The work is done on the system, and the weight sitting on the lid of the piston is going to come down in the surrounding. The capacity of the system to do work increases. When you are compressing the system, the capacity, you are increasing the energy, and the capacity to do work is increasing. Or we say the energy of the system is increasing. So when we have a compression, you can visualize, when you have a compression, you have a lowering in weight in the surrounding, the capacity to do work is increased, and energy of the system is increased because you're compressing the gas. When you are having expansion, it's equivalent to having a weight lifted up in the surrounding, and the energy of the system is decreasing, so it is less capable of doing more work than the previous case. So let us visualize what work is. Work is slightly defined differently when you are talking in chemistry. We take work is equal to force into distance. In this force is actually the opposing force we are looking at, we are working against. So since it's the opposing first force we are talking about, we always say W equal to minus F. Why? We are doing work against the opposing force, so we have a minus sign. And when we look into a expansive or compressive work, let us visualize a cylinder. This is the cylinder I've been talking about, where it can have insulated in all sides except the bottom. If you want to have isothermal condition, what happens is you have a piston here. This is, you can see the lid of the piston. This is going to move up and down. So what happens when you are having an expansion? When you are having an expansion, the piston lid moves by, say, distance dx or dz. Okay, let it move by dz. So this is the new volume after expansion. So how will you find out what is going to be the work done? Work done, what we have said, work done is equal to force into distance. Now what is this causing the lid to go move up and down? It is the pressure, which is the external pressure which is exerted on the lid. So the pressure is given by what? It is force per unit area. If it is force per unit area, okay, so the force will be the pressure into the area of the lid, right? Force is the force equal to, pressure equal to force per unit area. Force per unit area. So the pressure becomes equal, a force becomes equal to pressure into area, right? It becomes pressure into area. So now I substitute this force here in the expression of work. So it becomes P external, whatever we are going to talk about, what is P external, into A. And then the distance which is traveled, what is the distance it is traveled? It is dz. So we put in that value of dz. What is the value we have got? We have said W we are taking as minus, and the force which is going to be P external into A, this is the pressure which is exerted on the lid, into the area, into the distance which is moved, dz. So if you see A, this is the area of the piston, and this is the movement of the piston. So what it is doing when you are moving the piston from this to this, actually you are sweeping the volume from the entire area. This volume is swept. What is the volume? It is A into dz. So I can replace that A into dz by volume change. So if I can rewrite, what is going to be work? Work is going to be nothing but minus P external dV. Now, if the changes are very, very small, carried out very, very small, the infinitesimally small changes are being carried out when you are gradually expanding, then what we can do, instead of writing a discrete volume change, we have a change in, because each condition the pressure and volume is going to change. So we integrate from the initial volume to the final volume into P external dV. So whenever we are having a very small changes in the process taking place and infinitesimally small changes, then the pressure and volume keeps changing, and the changes are so small that we can call it a reversible process. So we can say that this work which we have got, integration from initial to final volume over the P external dV with a negative sign, is the representation of a reversible work. So the work done in a reversible process is nothing but the integration of PdV. Okay. Now work, if you have to remember the science convention, it is just opposite to what you take in physics. Work done on the system. Whenever the work is done on the system, there is a compression. So compression means the volume is going to decrease. And if the volume decreases, what happens? You already have a minus sign. This minus, it becomes a positive. So there is going to be a value which is going to be more than 0. It's going to be a positive value. When you have an expansion means volume is increasing. So if you are having an expansion work done by the system, then the volume is increasing. Remember the volume change only, then you can do the convention of the work very easily. So whenever we are talking about minus work, we are not talking about minus work as such. There is nothing as minus work. It is the work which is done by the system. Minus sign indicates whether it is the work is done by the system, nothing else. It is not a quantification which is minus. It is magnitude is always positive. Sign only represents whether it is by the work is done by the system or on the system. So whenever work is done by the system, the sign will be always negative, so the W will be always less than equal to 0. Whenever there is expansion, a compression, then the volume is decreasing, so the volume and W becomes positive, so W will be always greater than 0. This is the convention we are going to follow. So what I want to emphasize is I want you to understand what is P external. Always visualize the P external as a sandbag sitting on the lid of the piston. If you visualize that, there will be no confusion as to what the P external is. If there is a P external means a bag of sand sitting on the lid, that means if I want to have an expansion, and which is done very, very slowly, reversibly. That means if I have an expansion, I take off 1 grain of sand without disturbing the entire system. The system is completely insulated excepting the bottom. Now, if I want to expand the gas, what I have to do, if the gas has to expand, then this pressure has to be lowered, which is exerted on the lid. So you take off few grains of sand. This is what the reversible changes mean. The changes are so minute, it is equivalent to taking out a grain of sand from that bag. Now, when you want to compress the gas, you imagine you are adding these same grains which you have taken off one by one. So you can understand the system is an ideal system. You cannot really do that. You cannot take out a grain of sand or put back a grain of sand without disturbing the entire system altogether. So that your system is going to go off equilibrium. So what we are talking about here is the condition which is very ideal, and you visualize that ideal system as a sandbag sitting on the lid, and that is what is deciding the P external. So what is P external? P external is the force acting per unit area of the lid. So what is the force? It is the mass of the bag into G, the gravity. So the weight of the bag. Okay, mg is the weight of the bag, which is the force which is acting. So if you want to find out what is the force, P external into A, and P external is what? Mg by A, if you can understand. So what we have to realize that whenever we are doing an experiment of piston and gas inside, we are actually lifting a weight which is sitting on the lid. If you visualize that as the P external, all your problems will be solved as which is P external and what is P2 and becoming equal to P external. So let us see the work experiments, what we can do. You just see you have two conditions where this was the initial condition and this is the final condition. This is the mass of bag which is sitting on the piston, and this is a cylinder which is frictionless piston with sides insulated except in bottom. So what we have a mass sitting on this. Now what happens? What is the pressure? What is the pressure? What is the pressure? Force per unit area. What is the force? Mg by A. So mg by A is the pressure which is exerted by the mass of the gas, and that we call, let us call it as P external. Okay, mg by A is the P external. So always remember the P external, if you visualize, is the weight the sandbag is exerting on the area. That is going to be the pressure exerted equivalent to the P external. So what happens? You have initially some mass and the gas is at one temperature of PV and T, P1, V1, T1, and let it expand. Let it undergo a change in state so that the new temperature pressure values are T2, V2 and P2. Okay, so now you see this is expanded by some distance h. Now let us find out what sort of expansion this is going to be. The movement of the mg into h, px into a, that we have already said, this is the area, this is the force into the distance h. So this becomes the volume change. What I'm not in this we have already done. So what I'm interested in finding out, when will this gas become can expand? When can this gas can expand? The gas, there is some pressure inside this. Okay, so if it is an expansion, then what happens? This pressure should be much higher than the pressure which is exerted by the bag which is sitting on the external, on the lid. Okay, so what is going to be happening? Let us suppose, let it go expand. This P1 is much higher than the weight which is sitting on it. So if the pressure inside is high, it is going to push the lid, right? So it is higher than whatever is there. So it is going to be able to push the lid. So let it push the lid and come to this position. And now the gas is supposed to have a different pressure, and the pressure is supposed to fall because of the expansion. So P2 is the final pressure. And now if you want to have a balance, to if the how long will it keep going, expanding? If it is allowed to do it as per the P external, then what will happen? This was previously very high. Now it will keep rising till what happens? It is in the equilibrium, whatever the pressure is there inside, is equal to the pressure exerted by the weight of the sandbag. Okay, that is mg by a. Whatever pressure is exerted by mg by a, when it becomes equal to P2, then the gas lid movement will stop. So that is the pressure we are talking about. So when P external becomes P2 is possible when this pressure inside the gas is going to be balancing, or it will be equal to the mass of the weight of the sandbag sitting on the lid and is balanced. So what happens here? We have a movement of the cylinder right in this direction. So how do we plot? How do we plot the PV if we want to change, depict the entire PV conditions on a PV diagram? Because we had initial P, P1, V1, and finally we had P2, V2. I'm not saying the temperature is remaining constant. Temperature may be changing. I'm not putting in that condition right now. So what happens? Initially it was in some point 1, P1, V1. P was very high, V was relatively small, and it underwent an expansion. And what was the final state it came to? It came to point 2. So the P is finally this one, the final P. And what is your work done? It is minus P external dV. Okay. So what is the dV? dV is V2 minus V1. So this is the area. This shaded area is your work done. Okay. This is a process in which the expansion is taking place in one go. That is why I have written P2 V2 minus V1. If it had been taking place very slowly, I would have to integrate. Okay, so that would have been a reversible process. So when I'm not doing a reversible process, then I have a discrete change in volume, and that means this step is occurring at one go to this step. Okay, so the pressure is released previously it was held by some pin, and when the pin is released, what is going to happen? The pressure is going to push this lid up until the weight of the sandbag, whatever pressure that is exerting, is becoming equal to the pressure of the gas inside. Till that point it's going to move. So which point it is going to move? Till P2, the gas pressure in the final state becomes equal to the P external. That is the weight of the mg by A, which is exerted by the weight of the sandbag. So this is the area I get. Now if I say I want to carry out compression. Compression means, what does compression means? Compression means here this P external will be more. P external will be more than this one. Only then you can compress the gas. Okay, so the P external is much higher. So let the P external be high, and that P external is nothing but mg by A. That's the sandbag, whatever it's sitting on the lid, that is exerting the pressure. So how long will it continue? How long will it continue? Until what condition it will continue? Just imagine when P2 becomes equal to P external. When P2 becomes equal to P external. Here, suppose I had a state where P2 is supposed to be higher and P1 it was supposed to be lower. This is a lower pressure, and I put the weight down, keep it pressing, and I get, this is for only for the expansion process. The diagram for the compression is not drawn. The diagram for the compression would look something the opposite. It would be initially like this. P1 would have been here and P2 would have been here. Okay, so if you have a compression, that means this will be larger and this will be smaller. So you compress the gas, and that is possible only when the gas pressure is lower than whatever is there. If it is more, then it's going to push it up. So you have this has to be the mg by A should be much more than the pressure which is of the gas inside. So that is what I have written here. I have not drawn the diagram for the compression process. This is only for the expansion process, but you can imagine the compression process is going to be something very similar. But here this would have been P1, V1, T1, and this would have been P2, V2, T2. And this will come to a position where P2 will be equal to the pressure exerted by the sandbag sitting on the lid. That means mg by A will be equal to the P1. So that is how we are visualizing that. So what is happening? Initially we had a volume, state 1, and state 1 volume was higher, and gradually you compress. Compression means the volume is going to decrease. So you decrease the volume, you move along a PV path and decrease the volume. And what happens after you reach the final pressure? This is the final pressure you reach. So this is the final pressure you have, and corresponding to the volumes you have for V2 and V1, this is the entire area which is the work done on the system. So you see, when you are talking about the expansion taking place in one go, both of them are taking place in one step. There is no my number of steps involved. The number of steps, infinitely small steps we had said for a reversible condition, that is not existing. Only one step, one blow and the gas is compressed, and one blow the gas is expanded. So this, whenever they are happening in a jerk, any process which is happening in a jerk can be taken as a irreversible process. So this is the irreversible process, and this is also a irreversible process. And irreversible process, you have to make understand, it should be a condition where the pressure inside the gas is greater than the weight exerted by the sandbag sitting on the lid. Only then it will spontaneously push it up. Before that, it is going to be held by a piston. Now what happens if it is to be compression in a irreversible process? It also has to go in one step. Then what happens? The pressure of the external whatever weight which is sitting sandbag is much higher than the pressure inside the gas. And if that is the condition, then if the this is held by a pin, then as soon as the pin is removed, this gas will put a jump of pressure on the gas, and the volume is going to be compressed. Okay, so this is the compressed. You see the area in the compressed single step compression is a shaded area is larger than that of the uh, shaded area which we have in a expansion process. Expansion means the work is done by the system, and the compression means the work is done on the system. See, in thermodynamics, our purpose is to get or harvest energy. Okay, so whenever we are talking about work done on the system, who is doing work? We are doing, or surrounding means we are doing work on the system. We are not interested in doing work on the system. We want the machine to do work for us. So this is known as destructive work. Okay, this may be very large, but this is actually a destructive work because we are doing work on the system. Okay, now what happens if I do a expansion into vacuum? What is the expansion taking place in vacuum? That means the P external becomes zero. There is no resistance against which the volume is moving. If P is equal to P external is equal to zero, then what happens to the work expression? W equal to minus P dV. So the P expression becomes equal to zero. So for any free expansion, the P external is zero, so work done is zero. Okay, I hope you know that. Now suppose instead of taking a one-step process, which I had taken in a reversible step, I start decreasing the number of steps. Okay, so I start decreasing. This was the initial condition of the expansion. This was the initial condition of the compression. Now, instead of compressing from directly from A to B, I have taken steps to come in between. I take a P prime and corresponding to volume prime. Okay, I'm carrying out a expansion. Then I do an increment further and go to another P a double prime, and corresponding volume I take P double prime. And finally I get to the P2 and the V2. That means I've increased the number of steps. And if you see what is the work done when I'm coming from the initial A to this position, what is my final pressure? P prime. P prime into this volume change is the area of the work, which is shaded area is the work done. Now from this position, I come to this position. Now what is going to be the new pressure? This is going to be the new pressure. And this pressure corresponding what is going to be the volume change from here to here. So this is going to be my shaded area is going to be the work done. Similarly, when I take another step from P double prime to P2, then I make another step, and the volume change is corresponding to V double prime to V2. So V2 minus V double prime will be giving me the volume change, and the pressure which is going to be, what is the pressure? Final pressure is P2. So this shaded area will be my work done. So similarly, if I want to take out a compression um, in the same manner, you see I have started from B to A. I'm going to go to the compressed state, highest pressure condition. Instead of going from one step from here to here, I take the first from P initial to I take P prime. So P prime, the pressure is volume is going to decrease. This is the decreased volume I have, and then from there, that's the final pressure is P prime, and from that P prime I take the P double prime, and similarly I keep doing the changes from here to here. Okay. Finally, what do I get? I get a pressure of P2 here. This is the final P2. In between, I have got a pressure of P prime, and this P prime corresponding to P prime, I have this volume change. So this is my final pressure. This is my volume change. So final pressure into the volume change is going to give me the area, shaded area. So you see the amount of destructive work is actually decreasing when we are increasing the number of steps, and the amount of work which is extracted from the machine, that is work done by the system, is gradually increasing. So the more work has been produced in multiple step expansion than the single step expansion. Okay. And less work is destroyed in multiple step compression compared to the single step compression. Means irreversible work. When I'm gradually decreasing the in increasing the number of steps, then I can visualize that happening is the amount of work this is the area. It is gradually, it is not to the scale, but if you can do the scale, it will be something like this. This will be the area before, and gradually it is decreasing. The destroyed work is decreasing, and the more work is produced by the machine. So this is a system which is more relevant. Here W will be negative, here W will be positive. Now, if I keep increasing the number of steps, infinite number of steps I keep increasing, then what happens? I get so minute steps that I can say that the change in the pressure and each step I'm doing the increment is tending to zero, and the volume is also tending to zero. Now, if such a condition is put, then the maximum and minimum work can in the reversible process can be evaluated. You see, you increase the number of it is the expansion process. If you keep increasing the number of steps, gradually what you get a continuous area like this. And what is the condition? It is a reversible condition, and we are making very small steps, so small step that pressure is tending towards zero and volume is also tending towards zero. So how do we find out? We integrate that pressure PdV from V1 to the V final. So whenever we have to have the maximum work, we want to generate the maximum amount of work. And for generating the maximum work, we have to make sure that the P external should be always having the largest possible value at each step of the expansion. So we are carrying out a multi-step expansion, very minute step expansion, but for each step, the P external should always possess its highest value or largest value in each step. And that means what is P external? It's the sandbag sitting on the lid. So if this has to be always having its highest value, that means if I have to expand, some gas is going to expand. Okay. So how can the gas expand? The gas can expand if the pressure inside the gas is more. If the pressure inside the gas is, let it be P, then what should be the P external? Because P external should have its largest value. So the P external will be less than the pressure of the gas inside. But by how much? Because it's expanding, the gas is pushing the lid. So if the P external has to be maintained maximum, then it should be such that the P external is the difference between the P external and P of the pressure inside the gas is very minimum. And what is that? Let us say it is delta P. So if I say the P external is so small, is largest when you have the pressure of the gas inside the cylinder P minus dP, that means a very small difference is there between P external and P, and that should be always less than the P, because it's expansion. Expansion means the gas is to be pushed, and it can be pushed only when the P external is less than the pressure on the gas inside. But if it is too large a difference, then the expansion will take place in one go. So to make multiple step process, to make a reversible process, what you have to ensure that the P external is maintained the maximum largest value, but for that the increments of difference between the pressure which is exerting the piston to move and the pressure, the P external coming from the sandbag, are almost equal but only slightly different, and that slightly different should be the P external should be slightly less than whatever the pressure is inside the gas, otherwise the expansion will not take place. So that difference, let it be very small, delta P. So the P external will be always equal to whatever the pressure of the gas which is pushing the lid minus some amount of P, that is delta P. So if I integrate that minus P dV over now, putting this P external here, P2, V1 to V2, the final volume, or Vy to V final volume, with the minus sign is always remaining. So now I apply external. P external is P minus P dV, minus P delta P. So P minus delta P into dV. What it comes to? P dV minus P dV and dP. So it's a double differential, and if we ignore neglect the higher order differentials, because it's going to be very, very small, we can ignore that. So what we come down to is P, the maximum work is equal to the integration of P, this is the gas pressure, not the P external, the gas pressure into dV integrated over the initial volume to the final volume with a negative sign. Now for an ideal gas. For an ideal gas, what can we do? We can replace this P by nRT by V. Okay, and suppose it's an isothermal process. Isothermal process, if it is, then I can say this T is constant. So nR, n number of moles R into T is a constant, and only change is the volume. So what do I get? I put it in here, the value of V. It is in denominator is V. So what do we get? We get n minus nRT dV by V integrated over initial P to final V. Initial V to final V. So what will you get in that? You will get the logarithm of V2 by V1 into minus nRT. Now you can replace this in terms of the pressure, because you have the inert gas law and V is inversely proportional to P. So you can write down the P1 by P2, or with the negative sign gone, we can write P2 by P1 into nRT-ln. Okay. So let us see an example of one-step process, irreversible work. Irreversible work means P external becomes, suppose this is the initial pressure which we have. There are stoppers. Here we have stopper, here we have stopper. There is a mass sitting on the a sandbag sitting on the lid. Now, for the first case, you open this stopper, and if you open this stopper, it is going to keep expanding until the pressure of the sandbag pressure exerted by the sandbag is equal to the final pressure. So that is the condition. P external becomes equal to P final. So you can, for all discrete changes, whenever you have an irreversible process, always we are going to be replacing the integral. Here we had already always integrated when we have a reversible process. When we have a discrete or irreversible process, V is always delta V, a discrete measurable change. So what you have, P minus the P external becomes equal to the P final into delta V. Okay. Now suppose we have restricted expansion. So we say the pressure is the gas is expanding against say external pressure, and this external pressure is a fixed value. We have instead of balancing the weight, it is going to be going and hitting the second stopper, and this stopper decides the P external or the fixed pressure. So if again that will be equal to P external minus which is the fixed pressure. Now it becomes equal to the P external, because it cannot move further, whatever weight is there, because there is a stopper here. So the restricted pressure means you have a stopper along which restricts the volume expansion. So that will decide the final pressure, and that can be equated to the P external. So that will again give you P external delta V. When you are having an expansion against no weight in free expansion, then the P external becomes 0, the weight is not there, you see, becomes 0, and the work done is 0. See, all these are irreversible processes. Now, if you have a cyclic process, you can see, we have seen this, that in a cyclic process, if you have a work and heat, they are supposed to be path functions, so they are dependent on the path and through which it's performed. Suppose you have a cycle from A to B to C to A to 1 to 2 to 3 to 4 to again back 1. In the cyclic path, what is going to be the work done? Let us move from 1 to 2. There's no volume change. Work done is 0. And from here to here, what is the volume change? The volume change is V3 minus V1, V2, and V1 is equal to V2 because there is no volume change. So you can replace by V1. And then again you have a constant volume, there is no work, delta V is 0. And then again you have this process where you have the volume decreasing from final volume being V1 and initial volume being V4, and V4 is equal to V3, so we can write down V3. So if you go to the cyclic process, you can rearrange and you see P3 minus into V3 minus V1 is what is the work done. Now, if you have a reversible cyclic path along, say, 1, 3, and back to 1. So this is the path if we are taking is reversibly done. Then what you have, the volume changes from first initial V1 to V3, and the reverse is V3 to V1. Okay, so the W, if you take minus sign outside, then you can say it is V1 to V3, and the return is going to be V3 to V1. It will be just the opposite. So they will cancel off and it becomes 0. So you see, work may become 0. That is what I'm trying to say. If it's a reversible cyclic path, the work may become 0, but it is not necessarily that in all conditions you are going to have 0. Suppose you have a cyclic process, even a cyclic process, W depends on the path which is taken. So if you are choosing this path, it is becoming 0, and if you are choosing this path, it is not going to depend. It is going to not be 0. So if I look into the say the internal energy over the path, what is happening? Internal energy is equal to the work done plus the heat exchanged. So what happens? The internal energy being a state function becomes equal to 0. So minus W will be equal to the change in the energy transfer in the cyclic process. So what we can conclude, if you see this, I have comprehensively done this. This is the irreversible process. These are the irreversible processes. These are the irreversible processes, and these are the reversible processes. So if you compare from irreversible process going to the reversible process, what you are doing, you are actually increasing the number of steps, and infinitely number of steps if you are coming to, then you get a reversible process. You see what I have said before, in irreversible expansion, you are generating more work. So the work is reversible. If you are carrying out a reversible condition, expansion work becomes more in a reversible than a irreversible process. And what about the compression? Compression, you see, in irreversible step, you had, this is the area which was destructive work, and gradually the destructive work became decreasing as we increase the number of multiple steps, and then irreversible compression gave you this value. So you see, when you have a reversible expansion, the area of the shaded portion is equal. So in irreversible process, the work done in the reversible and irreversible process becomes equal to zero. Okay, equal, sorry, they become equal, the shaded area become equal. But for an irreversible process, you see, this is not equal to this, the area, the compression process, and the work done in the compression process and the expansion process is not equal to they are not equal. They are, the work in the expansion process, this is the expansion process, you see, is much less than the work in the compression process. Okay, so you can understand. So expansion means the work done in the by the gas. So here, if you see, the work done is much less in the expansion process than the compression process. So you can make out from the diagram itself. So work done on expansion by a system on surrounding, the sign is the negative, because the work done on expansion means you are doing work, but the system is doing work on the surrounding, operating between specific initial and final states and passing through and specified path is maximum work available for a system when the changes are taking place reversibly. So you can understand, for any expansive work done by the system, it is going to give you the maximum work when you carry it out reversibly. So that you see, the work done in the reversible process, the magnitude of work done in the reversible process is going to be more than the work which is done in the irreversible process. Okay. So because when you are talking about maximum work, you are talking about the number of increasing the number of steps, and so you can make out that the expansion and the compression works become equal, and the area of the shaded portion also shows you that when you are having expansion, then the maximum amount of work you can get, and if you are having a compression, the destructive work is the minimum, so you get whatever the work which is the shaded portion, which is for the work done by the gas. Okay. Work done on the work done on expansion by the system on the surrounding is is the work we are always looking into, and that will be maximum when you carry out reversibly. Okay. So let us see what sort of cycles we can have. Suppose let us connecting initial and final state. How is going to be the diagram looking at? Now suppose I am doing at a constant pressure. Constant pressure means the work is on the gas. You see, if constant pressure means I have to carry out a process where the pressure is held constant. What happens? You have P V2 minus V1. Here what you have? V2 is greater than V1 or V1 is greater than V2. When you are holding a pressure constant, what has to be changing? You have to integrate between V1 to V2 and with the negative sign. So if you take out the negative sign, it is P V1, V2, V2. I think these are things which is you should do it yourself. So you can see when this is the shaded area when you are having a constant pressure process, and when you are having a constant volume process, you will understand this is what you are going to have constant. This is the constant volume. Sorry, this is the constant volume followed by constant pressure, and this is constant volume. This is constant pressure followed by constant volume. And if this you are having, this is continuous change of P and V, and that will give you this sort of a expression, right? And if it is a gas is at constant volume, obviously there will be no change and PdV equal to 0. But if you are having a constant pressure, then you do not integrate. P is taken out. You do not integrate with the integral sign. You just put the P and you have the change in volume. So these you should practice. So if I have an isothermal expansion, what I do, I put W equal to minus PVD, P minus P external dV, and integrated from initial to the final volume. Put the value of P external being pressure of the gas minus small amount of dP for the expansion, and from there you can find out the maximum work is going to be minus P delta V integrated over the volume change. And if it's the ideal gas, then you can replace the V by the nRT by V, and nRT by V and into dV by V you get in the expression that will give you the ln term, ln V final by V1, V initial minus NR ln V2 by V1 or V final by V initial. At high temperatures, work done is more for the same volume of expansion. I think it is understood because the temperature is here. So you increase the more the temperature is increased, the greater is the work done. Maximum work is done in the reversible process. Irreversible process is the work is always equal to minus P external dV, while if you are having a reversible work, it will be always an integration of P delta V over the limits of the volume change. And if you are dealing with the ideal gas, then you can replace the P by nRT by V, and from nRT by V into dV, you can get the expression of minus nRT ln V2 by V1 or V final by V initial. So I will leave this for you to do, how to find out what will be the work. You just, one example I'm going to say, you can predict the work which is done. Pressure is 10 pascals, 1 meter cube, temperature is T. Now you have an isothermal process. What are you doing? Isothermal process means temperature is remaining constant, T is T here. And what you are doing here, you are changing the pressure from 10 to 1. That means you are carrying out an expansion, and the expansion will be done something like this. So this is the final pressure you have reached, and that pressure corresponding to that pressure, this is the P final, and corresponding to that you see the volume changes, and this shaded area will be you may be asked to shade out the areas on which the work done give the work done showing the shaded curve. So this is how you can do it. Suppose you have an isochoric process, in one isochoric process from temperature T, suppose pressure is 10 and it's going to 1 Pascal pressure. What happens? 10 to 1 Pascal pressure is what? You have a expansion, and expansion is not possible since it's an isochoric process. So if it cannot expand, what will happen? The temperature will increase. So temperature is T2, and from there you make a constant pressure condition, and after constant pressure you are expanding the gas from 1 to 10. So if you are doing that, what is the final pressure area of the curve? It is going to be the final pressure into the volume change. So this way you can do the expression and calculate the sign of the work. Finally, whatever the work is done by the system or on the system should be found out. So we have a little bit time for the energy. I'll just briefly go through. Total energy of the system is called the internal energy of the system. The change in internal energy is a state function, so it is always given by only the initial and the final and the initial state. The difference between the final and the initial gives you the total change in internal energy. We do not find out the total energy as such. We always calculate the internal energy change, because the total energy is actually depends on the potential energy and the kinetic energy of the molecules. So that energetics, we are not going to be absolute values, we are not going to calculate. Since E is U is the internal energy we are going to deal with, this is arising because of the molecular motions and intermolecular forces. You have this internal energy associated. So internal energy is the kinetic energy due to motions of the molecule, maybe translation, rotational, vibrational, and total potential energy associated with the vibrational or electrical field of the atoms in the molecules. So that is the microscopic level of understanding. We are not going to go into that. We are just going to look into the internal energy as a macro property. So we are going to deal with is the molar internal energy, means per mole. It's an extensive property. That means it depends on the amount of material which you are having. But if you are doing it per mole, then what happens? It becomes an intensive property. So the molar internal energy is an intensive property, but while um, internal energy as such is an extensive property. It depends on the amount of matter present. So it's a state function, depends only on the current state. It is independent of the history or through the path through which it is executed. It's an extensive property, and since it's a state property, state function, integral over a cycle will be equal to 0. Now, the exact differential, I have discussed the exact differential in great detail in the last class. So when you are having a function like u, the fundamental variable of u is volume and temperature. And volume and temperature, if you want to write down the total differential, it's a state function, so you should be able to write down the total differential. It will be given as a total differential of u equal to how the u is changing, change of u with volume at constant temperature into the total volume change, plus how the u is changing with temperature at constant volume into the total temperature. So this is what we are having. We'll take up the adiabatic process in the next class. Okay. Thank you.